idea. Oh. Oh, yeah, perfect. Thank you.
Okay. Welcome to the second lecture of our panel, and the title for today is Analysis Incursion into Quantum Field Theory.
Okay, thanks. Welcome back. So I've gone through all my movies yesterday, so there's no more movies today. So the plan is to actually do some math. And so the content of this lecture is, so you see, in some sense, it's closely related to what I was talking about yesterday, but that link is not going to be obvious today. So you can take it as a completely self-contained mathematical theorem. I'm going to explain what the theorem is about without worrying about the links to what I was talking about yesterday. And then tomorrow I will try to explain what's the link and how it's relevant. Okay. So the title mentions quantum field theory because the problem that I want to talk about actually goes back a long time. So it goes back to the sort of late 40s and then 50s and 60s. And it's what was called at the time the problem of overlapping divergences in quantum field theory. And I will also explain what this means. And you don't worry. So if you have no idea what quantum field theory is about, it doesn't matter at all. Okay, so you can just forget about these words, just take it as some mumbo jumbo that gives some kind of motivation. I'm going to try to state a clean mathematical theorem that doesn't refer to any quantum field theory or any physics. So let me first give you a very, very, very simple example of the sort of things that we're going to talk about. Okay, so take a function k, which goes from R to R, which looks like this. Okay, so here at the origin, you have a singularity, and then it's compactly supported. So say it's 0 after a while. And it's smooth everywhere except at the origin. Okay? And so it looks like, so k of x looks like x to the alpha for some negative alpha near the origin. Okay? And then you ask yourself, is there a reasonable way of defining a distribution which goes with k, right? So usually, if you want to interpret k as a distribution, you have to say, how does it act on test functions? And usually the way that you turn a function into distribution is by just saying, well, you integrate k against your test function. Okay. And now what's the problem here? Well, there's no problem as long as alpha is bigger than -1 or minus the dimension. Right? But as soon as alpha hits, say, -1 in dimension 1, then you have a problem, which is that this integral is not well defined anymore. Right? So obviously this integral doesn't converge. So this is not a good definition anymore. Now, what can you do about it? So in this case, it's relatively simple. So first you note that if phi actually happens to vanish in a neighborhood of the origin, then this is always well defined, right? And so whichever way you define it for general phi, you want to make sure that if phi actually vanishes in the neighborhood of the origin, then it's defined like that. Okay, you don't want to change this definition for those phis for which it already makes sense. And so you're really only allowed to change the definition somehow at the origin. Okay? And so the natural way of doing it here is to simply say, well, what I do is I'm going to, ooh, this is getting messy. Let's see. Wow. So, thanks. That one? Okay. Well. Okay. So here, there's an easy way out, which is to simply subtract here kind of a partial Taylor expansion. Right? The test function is always smooth at the origin. Right? And so one thing I could do is I could subtract some partial Taylor expansion at the origin. So I could remove here some k less than something. We'll see where we should stop. Of, well, simply the derivative, the kth derivative of phi at the origin divided by k factorial times x to the k dx. Right? So now what have we done? So first you see that if I go sufficiently far, then, so say k is less than, I don't know, some value, say beta, so, then this thing is less than x to the beta, or small values of x. And so if I make sure that beta is sufficiently big so that beta minus alpha ends up being bigger than -1, then this is integrable. Right? So then there's no problem defining that integral. The other thing you see is that if phi actually does vanish in the neighborhood of 0, then all of these derivatives are 0 and I haven't changed anything. Okay? So in that sense, it's kind of consistent with what I said before. And so the natural thing to do here is to actually, if you want, modify the definition as little as possible. So you'd want to stop here in a way as sort of as early as possible, right, to make the integral actually converge. And so you would take beta something like, you know, whatever it takes so that it sort of stops just somewhere between -1 and, right? Okay. Now, the aim of this lecture is to actually describe some sort of similar procedure, but where instead of just turning one kernel like that into a distribution, you want to actually give a meaning to sort of complicated multiple integrals of kernels of that type. Okay? And you want to give a consistent meaning to multiple integrals of kernels of that type, which you can, as here, in some sense, it should be as close as possible to the original meaning. And what we mean by this, well, we'll see in a moment what we mean by this, but it means essentially that there are, you know, all the relations that should hold do hold. Okay? So how do we set this up? Oh, so maybe first I should, before I start, I should give you sort of a tiny bit of history. So some sense, so the problem that's going to arise, so of course, the fact that you can do this, people have been knowing this forever. And the problem that will arise is when you actually have interactions of different kernels and they diverge in such a way that it's not completely clear how you should, you know, subtract the correct. This is a little bit like subtracting an infinite constant like times a delta function or times a derivative of a delta function, right? Sort of if k actually happens to be integrable, then a term like this is the same as testing phi against the kth derivative of a delta function, right? So what you really do is you take your distribution and then you subtract some linear combination of derivatives of delta functions. And in some situations, it's really not clear what's the correct way of subtracting these linear combinations of delta functions, and that's this problem of these overlapping divergences that arises when you compute transition amplitudes in quantum field theory. And so I think Dyson was one of the first in 49 to propose some kind of solution to this problem of overlapping divergences, and then Salam somehow worked it out in a little bit more detail, but in both of these cases, it wasn't really a complete solution. And then Bogolyubov and Parasyuk, so that's the BP of the BPHZ theorem, they wrote a paper in 57 where they essentially solved the problem, which was then somehow rewritten by Hepp in 66 in a way which is, if you want, more readable. And then in 69, Zimmermann somehow explained in more detail the sort of algebraic structure behind the cancellations that arise in these calculations. And then actually so the problem is the theorem that I'm going to mention, it's one of these kind of folklore theorems of theoretical physics or mathematical physics that are difficult to find stated in a clean way in the literature. So actually the earliest statement that I could find, which is anywhere near a sort of satisfactory general statement that you could recognize, is in a paper by Feldman, Magnan, Rivasseau, and Sénéor from 85. And then actually the algebra behind was actually clarified in a neat way around 2000 in a series of papers by Kohn and Kreimer. So I would call this the theorem that I'm going to try to explain today. So it's usually called, well, so in physics it usually goes under the name of BPHZ renormalization procedure. So let's call it BPHZ theorem. And so that's Bogolyubov, Parasyuk, Hepp, and Zimmermann. And so in order to formulate it, so let me try to explain what kind of multiple integrals we're going to consider. And so for this, we first need to introduce a notion of a Feynman diagram. So for me, a Feynman diagram is going to be the following data. So it's a directed graph. Okay, so you take a directed graph. It's allowed to have multiple edges, so it's allowed to look like this, for example. Together with, so some vertices are going to be distinguished, and so I call these legs, and I'm going to always draw them in red. So let's say here. So you can either say, well, you can interpret this as simply adding two more vertices to your graph, and then saying, well, there are some edges that are distinguished, but they will always have the property that, that vertex sort of sits alone at the end of that edge, and the edge is always pointing inwards towards the rest of the graph. Okay, so these red edges always kind of point inside. So it always looks like this. You can have any number of these red edges, but at least one. Okay, and the red edges are furthermore numbered. So say 1, 2, 3. And what we do, we also give ourselves a finite number of labels. Okay, so we have labels, say L. So that's just a finite set. And we're going to decorate each edge with a label and a multi-index. Okay, so on each edge here, we have a label T and a multi-index K, with T an element of L, and K a say a d-dimensional multi-index, and I've fixed there's some ambient space RD somewhere around, okay, and the D refers to that ambient space. And there is going to be a special label, so let's call it delta because it's going to essentially represent the delta function, okay, and so these legs, they also have a label of that type, but the label is always delta, so it's always of the form delta and say k. Okay, that k is of course different from that k in general, okay? So a Feynman diagram for me is just that data, if you want. So it's completely just purely combinatorial. But the way you should think of it is the following, okay? Is that now, first give yourself, for each label, give yourself a kernel which is sort of looks like this, okay? So let me write sort of k0 is going to be a set of functions. Well, it's a set of functions. So an element of k0 is a way of assigning to each label a function from Rd to R. Okay? So an element of k0, which I'm just going to call k, is really a collection of kt's, one for each label, except for the delta one. Well, the delta, sort of think of it as a delta function. And with the property that, so each kt, I'm going to assume that they are compactly supported, say in the ball of radius 1. Say in B01. And such that furthermore, they behave like some power law near the origin. And so what it means, I'm going to assign to each of these labels a degree, okay? And so we have a degree function that goes from L to R, and the degrees always have to be negative here. So let's say from L to R minus. And so you want it to be such that if you take, say, any derivative of kt, they're always bounded by x to the degree of t minus k. Okay, so basically it just means they behave like kt behaves like x to the power degree of t. Okay. And now given some k in k naught. Oh, and I'm going to, so there's going to be it's going to be convenient to also introduce k infinity. So k infinity, subset of k naught, is those that are smooth. Okay, so they still satisfy, say, well, smooth function always satisfies a bound like this. Okay, so it's just similar functions, but they're just smooth everywhere instead of everywhere except at the origin. Okay? And so now if I take such a smooth guy, okay, then I can associate to each Feynman diagram a distribution in as many variables as there are legs here, okay, in the following way. So I have a map which I call pi k, which goes now from the space of Feynman diagrams. So let me call, say, T. So T is just going to be all formal linear combinations of Feynman diagrams. Okay, if you want, it's the vector space generated by the set of all Feynman diagrams.
That K is that.
Sorry.
Everything is called K. So
Everything, oh yeah, so there's a curly, okay, so there are curly case and straight case. So the curly case are the sort of space of all.
The superscript there is the K.
So this K infinity is the same as that K infinity, which is the space of.
High super Ks.
Also, this K is the same as that K. Right, so you fix yourself a way of turning each, you fix yourself a kernel for each label, okay? Now, given that you've decided which kernel each label represents, there is a function, pi k, which goes from the space of all Feynman diagrams into the space of all distributions with the property. So here, this is going to be a direct sum where sk is the distributions in k variables. Okay? And of course, T has also a natural direct sum decomposition where Tk is the Feynman diagrams with k legs. Okay, and pi k would map the kth guy here into the kth guy here. And which were in the following way. So if I take a Feynman diagram gamma, okay, like this. Now this is a distribution, so I have to hit it with a test function. Now the test function here has as many variables as you have legs here. Okay, so in this case it would be 3, for example. And now the way you do is you just take a multiple integral over all, so let me call here, say, so V star and E star are just the internal vertices here, so I don't count these guys. And E star, the internal edges, so the ones that are white and not the red ones, okay? And so you just, for each vertex here, you have an integration variable, okay? So you have dx, but now x has components xv, and there's one xv for each vertex v here. And now what you do is you just multiply. So for all the edges, right? So an edge goes from, say, E minus to E plus. Then you take the kernel k corresponding to that edge. Well, you differentiate it as often as that label tells you. Okay, so each edge now has a label which tells you which kernel you consider, and it also has a multi-index which tells you how often you differentiate it. Okay, so you take the corresponding kernel, you differentiate it the corresponding number of times, and then you evaluate it at x e plus minus x e minus. So for every edge, you evaluate the corresponding kernel at this coordinate minus this coordinate here. And then you integrate the whole thing against your test function. But then again, here on all of these legs, you also have these labels, and they tell you how often you actually differentiate the test function. Okay, so here you take a, say, product, well, a D, D1, K1, up to D, say, L, KL. If you have L legs, phi of x, say, V1 up to x, VL, dx, where I call now this vertex would be V1, this would be V2, this would be V3. Okay, so I have this numbering of the legs, so it tells me which variable of the test function I consider here. Okay, so here I have just some big multiple integral. The special case here would correspond to a Feynman diagram like this. Right, so this would be just, in this special case, this integral just becomes, well, there's only one edge here. You take the kernel, you evaluate at the difference of these two variables. So here it becomes something like an integral of k of x minus y, phi of xy, dx dy. But now, of course, you can just, you can do a change of variable where you do a change of coordinates. So you have x minus y and x plus y. You just integrate over x plus y. And then making sense of that integral is really kind of the same as making sense of that distribution up there. Okay? So this is a sort of baby special case of this general kind of valuation, which now associates a distribution to every single Feynman diagram of that type. Okay? And now the question is there a canonical way of actually making sense of all of these distributions simultaneously for all Feynman diagrams for all kernels in case 0 and not just the smooth ones? Right? So here I assume that it's smooth, so then this always makes sense. If I only assume that my kernel satisfies this, then in general that integral won't converge. Right? So I will have a similar problem as here, that I have a big integral which diverges, except that now, of course, the divergence looks much more complicated. Right? So it's not just a simple divergence which happens when. So here the divergence, I know exactly when it happens. It just happens exactly when x is equal to 0. Okay?
So
yes?
in the physics problem, you need to do these things simultaneously for some reason. You couldn't just do it. There must be some reason why you have to do everything at once. For all possible Feynman diagram, I mean, that's quite a...
Oh,
it must have come from...
well, the thing is, so it's natural to want to do everything at once because, you see, so for example here, okay, this looks somewhat canonical, but it really isn't, right? I mean, I could have added, in some sense, I subtract like an infinite linear combination of delta functions. I could add finite bits to it, right? And then the outcome would change. Right? So in that sense, it's not terribly canonical. It's canonical modulo somehow adding finite linear combinations of delta functions. Okay? But then if you want to define this somehow simultaneously for all Feynman diagrams, then in a way what you see is that you have a very, very large object, and the degree of freedom that you have in defining it is much, much, much smaller somehow, right? And so in that sense, you end up with something relatively canonical in the end. Okay? And here, here it looks very canonical just because we've actually truncated all these kernels to make them compactly supported. Right? So if the kernel actually behaved also like x to the alpha as x goes to infinity, then if alpha is an integer, a negative integer, I could not take that definition because there would be one of the integrals that, well, it always diverges either at the origin or at infinity somewhere. So I have to do this truncation. And then there's a lack of canonicity because you have to choose where you do the truncation. So, the legs appear, so here, yeah. So in this K1 up to KL, they are the labels of the L legs, okay? And the V1 up to VL are the L vertices that are connected to the legs. Sorry? Well, so, you could think of this as being, another way of writing this is instead of looking at only the internal edges, you take all edges, including those, and then you take kernel, which includes the delta function, and then you would just have a phi. right? But then you look at what's the definition of what the delta function does, and it just does that. Yeah. Okay. So now we would like to have a way of defining this pi k for all choices of kernels and for all Feynman diagrams in a sort of consistent way. And the question, yes?
Does physics dictate how you have to do that or not?
No, so what's going to dictate what how I have to do that is, well, I'm going to give you a wish list of properties, okay? And they're going to be very natural properties. And then if you want to keep all of these properties, there's going to be essentially no choice in what you have to do, okay? But these properties, okay, so here they will have nothing to do with physics, okay? But of course, it also gives you nice physics. I mean, because in physics, what you want is that your randomization procedure can be implemented by just changing coupling constants in a Lagrangian. In the case of these stochastic PDEs that I talked about yesterday, you want to be able to implement a randomization procedure by just changing constants in the right-hand side of the PDE. And in both cases, this will actually be a consequence of the nice properties that I'm going to write down, even though these nice properties will seem to be totally unrelated to that. Okay? And they would just look like very natural properties of this valuation. Okay? So what's the wish list that we would want? Okay, so what do we want now, right? So we wanted, okay, so for every k now in the curly k0, okay, where the kernels are actually allowed to diverge. So I would want some valuation, which I call pi hat k, just in order to distinguish it from the pi k, right? The idea is that pi hat k should be some sort of a renormalized version of this pi k. And so I want this to be, again, a linear map from T to S, which preserves the grading. And I would like to have, well, so what are the properties that I would want of this map? Okay. So a first property is that, well, so it's a very basic property, right? So I didn't, here in my definition of a Feynman diagram, well, I just said it's an arbitrary directed graph. I didn't specify that it's connected, okay? So I actually have a natural product on my, so this space is really an algebra, because the natural way of multiplying two Feynman diagrams is just to look at the graph, which is the disjoint union of both graphs. Okay, so I have a natural product. So there's a product which goes from T to T, which is given by disjoint union. And similarly, there's a product which goes from the distributions in k variables times distributions in L variables into distributions in k plus L variables, which is basically just given by the tensor product. So it just in the usual way, right? So here you also have this, which is basically tensor product of distributions. In both cases, these products are not quite commutative, right? Because I have to actually order these vertices, and same thing for distributions. If you have, a distribution in 2 variables and 1 in 3, and you multiply them, well, you get a distribution in 5 variables, and then you have to specify which ones of the 5 correspond to the 2 of, and which ones correspond to the 3, and this would change if you multiply the other way around, right? So they are not quite commutative, but basically they are. And so you would want, of course, this valuation here preserves that product. Okay, so that's somehow straightforward. So you would want that guy to preserve the product. Okay, so I want that pi hat k of gamma 1 product gamma 2 is equal to pi hat k gamma 1 product pi hat k gamma 2. then there's a second property that I want, which is that if I delete, well, so first if you have a Feynman diagram like this, so it always gives you a distribution which is of translation invariant, right? So everything was always just functions of differences of arguments, except in the test function itself. But the thing that integrates against the test function only has differences of arguments. And all my kernels were compactly supported, right? So since they are compactly supported, I'm actually able to test this against test functions that are not themselves compactly supported, right? Because I already have some decay in the kernels. And so I can, for example, test against test functions that are just constant in one of the variables. Okay? And the natural thing here is to say that, well, if I delete one of the legs here, right, and then test this against this function, which is only a function in 2 variables, that should be the same thing as testing this whole guy against a function in 3 variables, which just happens to be constant in that argument, right? So that's, again, a very natural property, which is that somehow sort of consistent under deleting legs. And then there's another property which is very natural here, which is that, well, you want to satisfy, there's an integration by parts property, right? So whenever you have so for example, you take any of these any of these integration variables here, what you see, the part of the integrand that depends on that variable is somehow these 4 kernels. If one of these kernels happens to be a derivative, then I could integrate by parts with respect to that variable and hit the derivative on the remaining 3 kernels, right? And then you would want to get the same answer, right? Because the integral should not change if I do an integration by parts. And so you want here consistency under integration by parts. Then there's another, now remember in this case, there was a natural, so now this is going to be similar to the fact that here we said, well, it's very natural to impose that if phi vanishes in a neighborhood of the origin, well, then the answer should just be that, right? So in situations where it's clear that the integral converges, then the answer should be the answer given by that expression. And so it's the same, we would like to impose the same thing here, okay? And for this, you have to understand under which conditions on phi is it guaranteed that this integral actually converges, okay, which is now not as obvious. And so in order to understand this, well, it's maybe easier to understand the converse, which is when does the integral diverge, okay? Also, which here happens if alpha is less than minus the dimension of the underlying space. So what's the analog of this condition that alpha should be bigger than minus the dimension of the underlying space? And so here the correct condition is a similar power counting thing. So for example, what could happen here is that you have some part of the integral that diverges, but it doesn't diverge because, you see, so now here, for example, you have 4 integration variables. Okay? And the integral could diverge not because, say, all 4 of them become equal. So here, x equal to 0 corresponds to these 2 variables becoming equal, right? Because the argument is really this x minus y. So the argument being 0 is when these 2 variables collide. Right? So in general, you could have a divergence if some subset of the integration variables sort of collides. Okay? And under which condition does the sort of subset of the integration variables colliding give you a divergence? Well, you can if you take a subset of the integration variables, so say you take these three, okay, and so now you look at the subgraph that just spanned by these three integration variables, so it's the subgraph with these four edges. And now there's a natural total degree associated to this subgraph, which is simply add up all the degrees of all the edges. Okay, so you look at so if you take a subgraph, your gamma, I would define the degree of the subgraph as the sum of the degrees of all the edges. So say gamma bar. So here take the edges in E bar, which is all of the edges in gamma bar. You take the sum of the degrees of all the edges, and then the natural thing is to actually subtract from here the dimension of your space times the number of vertices of the subgraph minus 1. Why? Well, you see, in this case, the correct condition is that alpha should be, well, you have divergence if alpha is less than minus the dimension. So in other words, if alpha plus the dimension is less than 0. And the reason why you pick up once the dimension is because there's one integration of x, and that basically gives you somehow, well, if you're in dimension d, this integral here behaves like sort of radius to the power d in a small ball, okay? And now if you have, instead of one integration variable, you have 5 integration variables, then if you integrate over a small ball, you get a, well, not just radius to the power d, but to the power 5 times d, okay? And now if you have a subgraph with 3 vertices, it really effectively corresponds to 2 integration variables because everything is just functions of differences, okay? And therefore, it's like you integrate over balls of size of dimension d times number of vertices minus 1, okay? And so it's natural to expect that the integral is convergent if this degree is strictly positive, or at least that sub-bit of the integral is convergent if that degree is strictly positive, okay? And so now the natural condition for this integral to converge is to say, well, you know, look at all possible subgraphs like this, and then look at those that are actually negative, that have negative degree, and then you have to make sure that the test function vanishes if those variables collide, right? So,
Isn't the degree always negative?
well, so this part is always oh, sorry, plus. yeah. Okay, so now it can be both positive and negative. Okay, so so now the condition is, well, you want pi k hat gamma of phi equal to just pi k gamma of phi if phi vanishes when variables corresponding to gamma bar with degree of gamma bar negative collide. Okay, and implicit in this claim is that this integral does actually converge in that case. Okay, and that's true. It's something one can prove.
So this is for all gamma bars. You want
Right, you want this, right, so if you take a test function, so for example, you could take a test function which simply vanishes as soon as 2 of the arguments are the same. But it's not, yeah, sorry, it's a little bit, okay. So you want to make sure that you actually do have, that all the gamma bars that diverge do have at least 2 legs touch them, and the test function then vanishes. Yeah, so it's in that sense. Okay, so that's a natural condition. And then there's one more condition, which is that so you have another natural way of composing these things, is that actually if you have two distributions, you can always convolve them. And that's still true if you have distributions in several arguments like this, in the sense that I can just pick one of the, if I have two distributions that correspond to two of these Feynman diagrams, okay, and then I choose one of the arguments for the first one, which is like choosing one of the legs, and I choose one for the second one, and then I glue them together by just deleting the two legs and gluing the corresponding vertex here, then that corresponds to some operation of kind of convolution of the two corresponding distributions. And just as in the usual case, if you have a distribution in one variable, it's always possible to convolve two distributions. You can sort of convince yourself that that's always true by sort of putting all the bad stuff onto test functions.
That requires compact support, right?
Sorry? Yeah, here everything's compact support, yeah, so you don't have problems. Yeah. And so in the same way here, it's always possible to give a meaning to this operation of convolution where you somehow make two of the arguments equal, okay? And then again, you would want that valuation to satisfy, well, to actually be consistent with this operation of convolution. All right, so here you would want pi hat k of, say, gamma 1 convolved with gamma 2, where here convolution really means take the two diagrams and take, say, the last leg of the first one, the first leg of the second one, and glue them together. And then this should be pi hat k gamma 1 convolved with pi hat k gamma 2. Okay? And the last but not least property that we want would be continuity in K. Right. So, sorry?
In the K infinity case, what you wrote down, that distribution doesn't have compact support. It's translation invariant.
Yeah, okay, it has compact support in all other directions. Yeah. Sorry? 5, yes. So this here is not the 10. So this product here is the one where you take, so if you take two Feynman diagrams, right, with legs like this, so this guy times, say, a simple one. This one, with, say, numbering 1, 2, 3, 1, 2, would be the one where, so I stick this leg onto this guy here. So I get this, and I keep. Right, so you get, so if you have k legs here and l legs here, you get k plus l minus 2 legs here because you delete sort of the last leg of that guy and the first leg of that guy, which sort of stick together. Okay? And then you have to think a little bit. So that's in the case that the corresponding index here is 0. And if this is non-zero, there's a little manipulation you can do using integration by parts to basically always turn it to 0. Okay? So you can always make these indices 0 by integrating by parts sufficiently often. Okay. So now the claim is, well, basically there is essentially a unique way of defining a pi hat k which satisfies all of these properties. Okay? And so that's this BPHZ theorem. And so, oh, I've got 5 minutes left. At least I've got as far as give sort of a statement of the theorem, which is not too bad. Okay, so let me give you at least some clue of how this pi hat k is going to be defined. Okay? So you have to somehow find a way of modifying the definition. So if you just did nothing, right, then all of these properties are satisfied except for the last one, right, which is that you don't get continuity. You have everything's well defined for kernels that are smooth, but as soon as they become singular, in general, these things diverge. Okay, and so of course this last property is not satisfied. So here continuity is in the system of semi-norms, which is given by these bounds here, right? So that turns this K0 into a Fréchet space. So it's in that sense that you want that continuity. So the problem is just to get that continuity, right? So once you have that, but you want to find a modification which doesn't break all of these nice properties, right? And that's the problem, right? So that gives you a lot of rigidity. So there are lots of identities that are encoded in these properties. And so you want to modify the definition of your pi k in such a way that all of these properties are still true, but you somehow get that continuity. Okay?
I guess that corresponds, you were talking about the continuity yesterday.
Yeah.
Relates to that continuity.
Yeah. So it's exactly the same. Yeah. And so what you look for is a map M, which might depend on K as well, which will depend on K, which goes from T to T. Okay, so it turns a Feynman diagram into possibly a linear combination of Feynman diagrams, such that I can just define that guy as pi k mk. Okay, and so now the problem becomes, what are the linear maps from T to T first that actually preserve all of these properties? Okay. And then, of course, what's the right one that I have to choose that gives me the continuity? So there are kind of two problems. And so let me just sort of show you what kind of maps preserve these properties. Well, you can sort of more or less guess it already somehow from here. So what did we do? Here, we essentially replaced this Feynman diagram with, if you want, indices somehow, T0, delta 0, delta 0. We replace this by itself minus this integral of k, just integral of k times, the first term here, the term at k equals 0, it's really just a delta function which hits phi. But the delta function hitting phi is really actually encoded by the Feynman diagram that just has two legs and doesn't have any sort of internal edges, right? That would correspond to just the delta function with labels 0 and 0. And then the next term is a derivative of a delta function, so it's somehow the same thing, but with a label, with a non-zero label on the legs. Right? So what we've done is we replaced that guy by a linear combination of guys that were obtained by simply collapsing this bit onto a point and then maybe hitting the outside with derivatives. Okay? And that's the general procedure that you do. Okay? So what you do is you simply look at all possible, so if you have a general diagram, you look at all possible subdiagrams that are divergent in that sense, in the sense that this degree here is negative. Okay? And then you collapse them to points. And you possibly hit the outside with derivatives, and you hit it with as many derivatives as you can fit into this without making the degree positive somehow. Right? So if the degree is sort of between -2 and -3, that you can put up to 2 derivatives outside.
That doesn't make it unique, so you have choice. That
So
suggests you have some choice, or you put all possibilities. Because there's a number, you have choice in how many derivatives you can.
No, so you sum over all possible.
Oh, you sum over
So
all
you sum
possible-
over all
okay,
possible
okay,
ways of
okay, that
adding.
makes it-
Right. Yeah.
So
Okay. So
the K here is from K infinity or from K zero?
so here the K would be, say, from K infinity. So these guys will make sense for K infinity. And then the point is that you want to choose a way of choosing that map so that so that this guy becomes continuous in K0, okay? But neither of these two factors is continuous, right? So of course, this guy obviously is not, and therefore that guy cannot be, because, but the product will be, okay? So the point is to find the way of, okay? Yeah.
So I'm a little worried about the integer powers, the integer negative powers.
Um, Well, so it's not a problem because we've assumed that things are compactly supported, right? So you actually go up to the boundary somehow. Well, so yeah, in some sense, you don't really overshoot. So if, for example, here, if it's exactly -1, then you would still have to subtract the first term, right? If it's exactly -2, you would subtract the first term and the second term, et cetera, right? So you go exactly up to. Okay, so you look for maps. So MK is of the form, well, extract sort of, or collapse. Well, no. Collapse subdiagrams gamma bar with degree gamma bar negative and hit outside with up to absolute value of degree gamma bar derivatives. Or maybe low, well, I don't know, maybe nearest integer upwards or lower. Okay, so you have to find the right one, but whatever, you see what I mean, right? And now, of course, you're going to obtain always linear combinations of that type. And then you have to figure out what are the coefficients. So now the coefficients is basically for each of the, now you have to, it's clear that if you have two different Feynman diagrams where you have the same kind of subdiagram that diverges, then you would want to pull it out in the same way, right? So you would want to have, you collapse it, and then you also have these derivatives, and you get a linear combination of diagrams by collapsing these divergent subdiagrams, and the coefficients that you put in front of this linear combination should be the same, whatever you have outside of the thing that you've collapsed, right? It should just depend on the shape of the subdiagram that you've collapsed, okay? So now you have to find a good way of assigning coefficients to all of these subdiagrams that might collapse, well, plus, the sort of various partial derivatives that you also hit the outside with. Okay? And so now the point is that there is exactly, so the claim is, well, so first, if you do this, so if you look at a MK of that form, then all the properties 1 to 5 are going to be preserved. Okay, so it's, for some of them it's obvious. It's, for example, it's not obvious for the integration by parts thing. Okay. But if you impose a certain, also like an integration by parts identity on the values of the coefficients of the linear combinations that you pull out, then you can guarantee that the integration by part is still preserved. Okay, so you also end up, imposing sort of algebraic conditions on the space of these coefficients that you pull out, but you can do this in such a way that all of these properties, 1 up to 5, are preserved for pretty much any choice of assigning numbers for these divergent subdiagrams.
That's so obvious.
It's not obvious. It's not, yeah. It's not terribly difficult to show, but you have to sort of sit down for an hour or so. Yeah, for some of them, I mean, it's sort of obvious for the first couple things, right? It's not so obvious for that one. It's basically obvious for this one, sort of by definition. And it's, again, not so obvious for that one. But now you have to choose the correct way of choosing these coefficients. And the claim here is now that there's exactly one way of choosing them, which has the following property. So there exists exactly one choice of now your mk, such that the following property is true, that if you look at your pi k mk, so you take a Feynman diagram so that the gamma itself has negative degree, okay? And it's connected, so you only look at connected things. So, and then you hit it with a test function which is actually a polynomial. Okay, and since, well, at least in the directions which are right, so there's always this translation invariant that you can kind of quotient out, but it's a polynomial in all the other directions. And the claim is that there is exactly one choice which has the property that this is 0 for all phi which is polynomial, and such that the degree of gamma, well, computed in the same way, plus the degree of phi is less or equal to 0. Okay? So there's exactly one choice that does that. And then you choose this, and the claim is that magically it actually gives you that continuity. Okay. So if it's fine, it essentially says that, so you have those guys that diverge. You say, well, essentially you have some divergent integral. There's no natural way of assigning any value to it, so you just assign the value 0. That makes it somewhat canonical. Okay? And then it turns out that these expressions sort of encode exactly those divergence integrals that you have to fix to some arbitrary value. So because instead of 0, you could have chosen some other value. Okay, so the fact that it's 0 here is just, it makes it more canonical. Okay, but it's essentially irrelevant. You can fix the value. But then this is enough to uniquely determine that map, modulo all the constraints that are sort of given by preserving all of these properties. And furthermore, it determines it in such a way that this actually becomes continuous. Okay, and that's of course the non-trivial part of the theorem, is to prove that continuity. Yeah? So.
Presumably the uniqueness helps in the proof of the continuity.
Not so much. The thing is, there's an explicit formula for this, right? Which is this, right? So there's a somewhat explicit formula for this guy, which is this famous, the analog, at least in this context, of the Zimmermann-Forrest formula. Okay? And so you have an analog of this Zimmermann-Forrest formula, and then you have various ways of resumming that Zimmermann-Forrest formula, which sort of give you the continuity. But yeah, okay. So I think so I meant to give you a few hints of how you actually prove this. But yeah, so I think essentially, okay. So just to give you a tiny bit of a clue, so what you have to do is that enormous integral, you have to sort of break it into domains. You break it into lots of little domains where you fix essentially the scales of all possible distances that appear between the integration variables. And there's a nice way of organizing that. In some sense, as long as you have just finitely many points, every metric space is sort of the same as an ultrametric space. And so you have sort of a nice tree structure. And in that way, you can break this big integral into essentially a sum, where you sort of break the integral into sum of pieces over these domains. In each domain, you somehow know which distance, you know sort of which way the triangle inequalities go on each of these domains. Okay, so which distances or which sums of distances are larger than other ones. And then you separately, for each of these pieces, so this expression becomes a enormous sum over various linear combinations of sign and diagrams. You have to resum this in the right way depending on the piece that you're looking at. So on each piece, you resum that thing in a different way in order to make apparent the kind of cancellations that you have here, right? So the cancellations of that type in a way, okay? But now here, what really happens because of these overlapping divergences is that the cancellations that appear might be different, in different regimes, in the sense in different point configurations here, right? Sort of depending on which distances are much smaller than which other distances. Okay. So, I think I would stop here for today. Sorry for going over time.
Question makes any sense or not, but this seems a lot more canonical, but is there some sort of sub-answer where you have fewer diagrams and you have a different
sorry, if you have
a different renormalization, if instead of having to handle every possible interaction, you want just some family of interactions that are allowed? Whether that makes sense as a question.
Yeah, I don't think it really changes much here, actually. No. Yeah.
But it would seem that, it would seem that you gave up on saying, oh, maybe that's, I don't know, you wanted it so that it just turned out to be this integral in the case when
your test functions or the right, yeah.
So that gets built into this operation MK.
Well, so that's somehow part of the. You see, since the operation MK looks at divergent subdiagrams and sort of collapses them, right? And so it means that if your test function, so this integral makes sense basically if your test function is such that it prevents these collapses, right? And so since you only add terms where you have these things that are collapsed, well, you only add terms that then end up being zero when you integrate it against the test function, which vanishes, when these collapses take place, right? So in that sense, this becomes automatic, kind of, yeah. Yeah.
Is there some way to extend this to the case where, so that you're not just having this estimate, but you have something that looks like more like the kernel of the pseudo-differential operator, where you have some extra cancellation in the top order.
He has no cancellation.
No, I know he's no cancellation, but if you looked at a situation where there was cancellation.
Right, so what can happen is that because of extra symmetries, you would know that some of the constants that show up are actually zero, right? So that's what often happens. So that here, the theorem was completely general, but it doesn't really tell, it's explicit in the sense that there's a formula for this guy for any smooth k, but then depending on the situation, well, you might only care about Feynman diagrams also having some additional symmetry, or Ks that have some additional symmetry. And then depending on situation, well, this guy, the effect might actually be to be 0 or to be just the identity or the, right? So depending on, so for example, right, like here, if this function happened to be an odd function, right, then even if it blows up, right, then it's like a principal value. And in that case, the first randomization constant here would just be 0, right? But by symmetry, right? And that's somehow not encoded in the statement because the statement is very general. But then you can kind of see in a way. So the thing is that, so you have a nice group structure of the, so yesterday I mentioned there was sort of, in the statement that I put up, there was some mention of some Lie group, which is sort of the Lie group modulo which the notion of solution is canonical. And it's sort of the analog here of the group of maps, so D maps M, which have, which are of that type and which preserve all of these properties, happen to form a group, which is not completely obvious. So it's not too difficult to convince yourself that if you compose two of them, that it's again a map of that type. It's not so obvious that the inverse is again a map of the same type, but they are actually. So they actually form a group. And it's basically that group somehow, or the analog in the SPD world of that group that showed up in the statement yesterday.
But you said that group was nilpotent, I remember.
Yes, and here that group is also kind of nilpotent. It's locally nilpotent. Yeah, because there's a grading, right? I mean, there's a grading. Well, so there are lots of gradings around here, but the relevant grading is the grading by edges of these subgraphs. And then that's actually a grading for that for the Lie algebra that generates that group, and it's nilpotent in that grading. Or in that case, it's sort of locally nilpotent because the whole thing's infinite dimensional, but yes?
Is there a clean description of the Lie algebra of that group?
Yeah, so sure. I mean, yeah. But so there's a clean description of the universal enveloping algebra, actually. Right, so the thing that you actually end up building is the Hopf algebra, which is kind of the universally enveloping algebra of the Lie algebra. And that one, you have a very clean description of that. And it's basically the product. So it's the dual of the thing where the product is given by the product of sort of concatenation. So in some sense, the generators are indexed by graphs of the same type but without the legs, and some additional decorations which somehow, count kind of the derivatives that you throw out. And then you have a product which is, again, simply putting these guys next to each other, which is commutative. And you have a coproduct, which is essentially given by these procedures of extracting subgraphs. And that gives you a Hopf algebra, and that Hopf algebra, also the dual of that Hopf algebra, is the universally enveloping algebra of that Lie group.
But that's the Hopf algebra that plays a central and primer
It's not, no, it's not quite the same.
Okay, so
It's not quite the same Hopf algebra. So the Hopf algebra that shows up in Kohn-Kreimer, it's more related to the resummation procedure that shows up when you try to prove this thing. So there's, yeah. So the Hopf algebra in Kohn-Kreimer, so it's this Hopf algebra of trees, right? And so what are the trees in this business? So there are no trees so far, okay? So the trees are collections of divergent subgraphs that are all related in the sense that for any two divergent subgraphs, either they're included in each other or they're disjoint, okay? And so then that gives you a tree structure. And then the Hopf algebra of Kohn and Kreimer is the one that sort of tells you, well, Okay, that tells you how these guys behave, essentially. But it's slightly different. It's not the same as that one. I mean, it's somewhat related, but it's certainly not the same.
Well, maybe we let people go here. And Martin is here, so I guess you can talk to him. He has an office here, and he's going to be here tomorrow, so we can continue tomorrow. Maybe also questions about